Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to do a nuclear binding energy practice problem. In the last video, I taught how to do this step by step, and in this video, I'm going to do it a little bit faster just as a practice problem. So if you want the details, go to the other video. If you want to see how this is done very quickly, go ahead and continue watching. But I'd like to see if you could figure out the nuclear binding energy per isotope, per mole, and per nucleon for a neon 21 isotope. Okay, if you've watched the other video, at this time hit pause, okay, and then go ahead and try to solve this problem. When you come back, I'll be working on the problem. Okay, so hopefully you've worked through the problem at this point, and the first thing that we're going to do is we're going to start out by writing a good equation. We know that neon 21, if we're going to break it up into its individual nucleons, it's going to end up making 10 protons and 11 neutrons. And we need to total up the mass of the 10 protons and 11 neutrons. And if we do that by using the mass of the proton and the mass of the neutron, so we got 10 of these and 11 of these, we find out that the mass of those individual parts is going to be more than when we have it binded together in the nucleus. So the individual parts, collectively, it comes out to a mass of 21.16806 AMUs, okay? And what we're going to do is we're going to calculate the mass defect by taking the final minus the initial mass. So this is the final mass. This is the initial mass. So go ahead and subtract these two numbers. 21.16806 minus this number over here will give you a mass of equal to 0.1796 AMUs. Of course, we're going to convert this over into kilograms, okay? And we're going to do that by taking the AMUs into grams, then the grams into kilograms. This is going to be Avogadro's number, 6.022 times 10 to the 23rd AMUs for every gram, and then there's 1,000 grams for every kilogram. So in kilograms, this is going to come out to be 2.9824 times 10 to the negative 28 kilograms. We're going to take this and we're going to plug it into E equals mc squared. This is going to be the mass. The speed of light is equal to 2.998 times 10 to the 8th meters per second. So this number times this number squared is going to give me the binding energy that's holding one neon isotope's nucleus together. And that energy comes out to be 2.681 times 10 to the negative 11, and that's going to be joules, okay? And that's on an isotope basis. So that's per isotope. Now, at the beginning of the prompt, I said, hey, we're going to figure out the binding energy per isotope and per mole and per nucleon. Okay, so to figure out this on a per mole basis, we're going to take that number and multiply it by Avogadro's number, okay? And if you do that, you get this number of 1.614 times 10 to the positive 13. And that's going to be joules per mole. And then I had to take this number, and if I was going to find out how much energy per nucleon, well, we got to figure out how many nucleons are in the neon nucleus. And there's 10 protons and 11 neutrons for a total of 21 nucleons, because a nucleon is just a subatomic particle that's inside the nucleus. And I got 10 protons and 11 neutrons inside the nucleus. So we're going to take this number and we're going to divide it by 21, because there's 21 nucleons in this isotope. Okay, so on a per nucleon basis, if I take this number and I divide it by 21, I get the answer of 1.277 times 10 to the negative 12, and that's going to be joules per nucleon. Okay, so we got a per isotope, per mole, and per nucleon basis as far as the binding energy. If this video has helped you, please give it a like and subscribe. Leaving that comment really pushes this algorithm to other students that might be interested in learning some chemistry.